okay, one of the aim of this meeting is to understand the diversity of the strategies between all these organisms we heard today. And I wanted to have your feeling of what you heard today and what's the more important things, what is your message? And that's one thing. And do you have a question in terms of modeling, because we have some modelers in this audience, in terms of 3D modeling or any kind of modeling? And okay, that's all. So Deborah, would you like to start?
No, I think from the diversity of models that we saw today and potential mechanism, I think, yeah, it's going to be hard to define a simple model of transgenerational or intergenerational heritability. It seems to be like a case-by-case study. Yeah. Even within the same organism, yeah.
Maybe I'll try to bridge what we see in plants and what you guys see in using mammalian models. I mean, the notion of reconstruction, and I don't know if it extends to C. elegans as well, I think is a very important one. So what at a macroscopic level may look like, faithful transmission may actually go in every single system through a reconstruction process. And I'm sure if this is the case, and there was plenty of modeling to be done on how do you recapitulate this whole range of possibilities, for instance, with your metastable alleles from one generation to the next. How do you, I don't know how far you can extend this analogy with C. elegans, but that's what I want to see. And even though in plants it looks as if indeed we do inherit demethylation patterns, we haven't actually got data for the oocyte. We have more data for the sperm, but for the oocyte, it's more by proxy that we do that, by looking at just at the zygote and a few stages after. Maybe there is reconstruction there too. And this reconstruction involves small RNA, so that's of course something extremely prominent in C. elegans. That's what I can say.
I think I agree with the idea that there won't be a single model. Because it's a complex phenomenon, there won't be one condition to look at, but I think it's important to look at different conditions across different developmental stages, because what, for instance, Deborah has proposed, it could be that there are time window, depending on the species, which may be more sensitive than others, a tissue which may be more sensitive than others. Now with single cell methods, I think it's very important to really try to focus a bit more on, to at the same time to keep an open mind by not focusing on one mechanism or one factor, but at the same time also looking more specifically at individual cells and germ cells. Even if we may consider that a sperm cell equal another sperm cell, that's not true. There is probably a lot of variability. So I think it makes the task more complicated for us, because we have to look at all these potential factors in different cells. But I think it's only like this that we'll be able one day to see perhaps a bit more clearly what's going on. For me, what's very satisfactory is to finally see that the concept starts to be acknowledged, that there are still a few dogmatic people who don't believe in it and would say, no, indeed, it's probably only genetic, you just not have looked deep enough. There will always be people like this. But the fact that there are more and more papers in different species confirming the transmission across generations, I think it's a good thing. We have, however, to be careful of what we are talking about. There are many models where exposure is right at the time of breeding, so where, again, mechanisms may be different depending on whether the germ cell has still some of the exposure, like high-fat diet. If it was just at the time of breeding, then it's probably another type of mechanism than something which happened weeks or months before. So I think there is room for many approaches, many concepts. We should really not focus on one model, but we try to consider different models. And what you said, the chromatin organization, we tend to think of one gene, let's say DNA methylation, perhaps a long non-coding RNA which will bind to the chromatin and modify it, but we have to think really 3D. And what happens here may also influence what happens on the same chromosome or even on another chromosome. And chromatin looping, the movement of chromosomes, I mean, something which could eventually keep a message. And methods also chromatin opening, methods like ATAC-seq in combination with RNA-seq could give more and more information. Maybe it's a bit confusing what I said. There is a lot.
I don't think so. No,
I think the matter is a bit.
The matter is complicated.
It's complicated.
Yes.
Okay. I think what I can take out of today is that there are many mechanisms. We all knew that. They seem very different, and they also differ across species, which is very interesting. And the question, I think I've asked this question in my talk, but the question is, why are there so many mechanisms? And how did they evolve? And this is something that we heard today too. Is there contribution there to epigenetic inheritance? Is it accidental, or is it something that's sometimes adaptive? Is it something that's been co-opted by evolution to facilitate adaptation in some situations? So I think there are very interesting questions in this area. Yeah.
Okay. Thank you.
Yeah, I think I agree that predictable from generation to generation and reconstructed from really what just starts from two cells that have one state or two states because they have two chromosomes, but it's methylated or it's unmethylated, and that's that's a 0 and a 1 that I think lends itself quite well to modeling. When you just then grow that into a whole organism, and you can talk about different developmental time points and when a particular event has to occur for you to see that long term down the line. I think is a great opportunity to mix sort of mathematical modeling and biology.
So I think what's common is we all try to chart the boundaries of epigenetic inheritance, and we see how difficult it is. I mean, for example, if work on RNAi have started not with C. elegans but with C. briggsii or some other closely related species, we wouldn't found anything not inheritance and not potent RNAi. So I think it's extremely important to choose the right model and to acknowledge the differences, not even between plants and mammals, but even between subtle differences between species, and we should somehow also, I think, abandon the ideology, which is very strong on both sides. Some people are very eager to find what they want to find the transgenerational effects, and other people are very eager not to find them. Yes, because it
Exactly.
also, when we talk about models, and
point.
then it messes up the models of population genetics completely. Nothing holds, and I think that what the model should somehow include, which is very difficult, is not only the mechanisms of inheritance, which is but also the ecology, the way that germ cells are defined in different organisms. It's very different, and it really affects which organisms can and cannot inherit, and the sexual strategies. All of this should somehow be integrated into the models, and it's very challenging.
Yes, thank you. Okay, thank you very much for everything. So I think today's meeting is closed, and thank you so much to yeah, but maybe you have a question, but thank you for you. Other questions? Maybe you are exhausted, but of course.
It's crystal clear.
It's rather crystal clear. Yes, I think so. No, but thank you so much for your participation. Thank you.